Hello everyone, myself N.Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So today we are going to have a session on energy methods which are subjected to bending and twisting. In the previous sessions, we have seen the analytical method in which we have seen the bending of thin plate which are subjected to bending, shear and transverse loads, and along with that we have seen combined bending and in-plane loads also, and we have seen bending of thin plates with small initial curvature. Now in this we are going to see all that whatever we are getting the results. Let's try to see in the other method, that is the energy method. Okay, so now the learning outcomes in this method are the students are able to derive the expressions for strain energy which is subjected to bending and twisting, and the students are able to analyze potential energy of the applied loading. So strain energy. So before we go into this session, let's try to define strain energy. So strain energy, how it is defined, it can be defined like any external force that is acting on the body, then the body is going to deform and the energy is going to store in the form of strain energy, and it has got various expression, that is strain energy which is subjected to axial load, and strain energy that is subjected to bending moment, and strain energy that is subjected to torsion, and so on. So therefore it has got different expressions for whenever the application of the load is changed. So there are two types of solutions that are available for the thin plate, and one is a exact solution, and in which the deflected form of the plate is known, and then the second one is the Rayleigh ridge method, and which assumes an approximate deflected shape in the form of a Fourier series, and which are having the finite number of terms which are chosen to satisfy the boundary conditions of the problem and also to give the kind of the deflection pattern expected. So these are two solutions. In the first method you are going to get exact solution because you know the deflection shape of the plate, and in the Rayleigh ridge method we will assume an approximate deflected form of the plate, and it has to satisfy the boundary conditions of the problem, and then you are going to get the deflection pattern. So now let's try to understand the strain energy produced by bending and twisting by considering these two diagrams, in which a small element of delta x cross delta y of a thin plate which is of a cross b as shown in the elevation in the xz plane in the figure. So when you see this xyz plane and it is shown in the elevation, so let's try to consider the two moments that are applied, that is mx is applied over here and mx is applied over here. So two moments, that is mx, are acting on the two edges of a thin plate. Now let us try to assume, if you try to draw a tangent to this moment, and let us assume it has a slope of dou w by dou x on the left hand side, and it has got incremental slope on the right hand side, that is as dou w by dou x plus dou by dou x of dou w by dou x into delta x. So this is a direct load, and when you try to take the shear component as well, you can see the right side diagram, that is XOY plane, and in which you can see mxy is the moment that is acting and a twisting moment, and on the other edge it may act with increment, and similarly mxy is acting here and mxy here increment. So let's try to understand only two components, that is mxy, which is acting over this edge and this edge. So let's try to see the component mxy is that is the twisting moment, and in which it is making an angle of dou w by dou y with respect to the vertical edge, and on the other edge opposite to it mxy is making an angle of dou w by dou y plus dou by dou x of dou w by dou y into delta x. So these are the two diagrams which we need to understand to write the further equations. So the bending moments mx per unit length are applied on the delta y edge, which we have seen, and it produces the change in slope. So here mx we have got dou w by dou x, and here mx we got dou w by dou x plus dou w by dou x into dou w by dou x of delta x. So when you try to take, this is one slope and this other slope, and if you take the change in slope, you are going to get the change in slope as delta square w by delta x square into delta x. So this change in slope or relative rotation of the ends of the element is negative as the slope is decreasing with increasing x. So you can see here as the slope, when the x value increases, the slope decreases. So therefore, it is taken as negative value. And therefore, if you try to write the strain energy expression due to this bending moment, the bending strain energy due to mx is given by half into mx into delta y and the slope. So it is just like half into moment into slope. And moment here we considered mx per unit length, so we have to write by multiplying with its edge length, that is mx into delta y, and the slope we have seen is minus dou square w by dou x square into delta x. So this is the bending strain energy due to mx. Next, similarly, if you try to consider the yz plane, you can write the contribution of my bending moment also. So therefore, the contribution of my bending moment for the bending strain energy, it can be written in the similar manner, like half into my into delta x of minus dou square w by dou y square into delta y. So these are the two contributions of mx and my bending moments for the strain energy. And next, if you try to write in the similar manner even the twisting moments contribution also, so you can write half into mxy into delta y dou square w by dou x dou y into delta x delta y, so into delta x, and then the next one you can write half into mxy into delta x dou square w by dou x dou y into delta y. So these are the contributions which you can write with respect to mxy, and when it is applied to the delta y edge, and you can write the contribution of mxy when it is written on the delta x edge, contribution on the delta x edge. Now next we are going to add all these contributions, mx, my bending moments and mxy contribution, and if you try to write as an equation, so you can write half into minus mx dou square w by dou x square minus my dou square w by dou y square plus 2mxy dou square w by dou x dou y of delta x delta y. So this is the total strain energy of the element from bending and twisting. Now we have the previous equation from the total strain energy, that is the equation what we have here, the total strain energy. When you try to substitute for mx, my and mxy from the previous equation, and it gives the total strain energy of the element as d by 2 into, so here earlier we have the equation mx equals to minus d into dou square w by dou x square plus nu into dou square w by dou y square. Similarly, we have my equals to minus d dou square w by dou y square plus nu into dou square w by dou x square. Similarly, we have expression for mxy. So in all these, if you try to write all these equation and if you try to write the total strain energy of the element, so you are going to get this equation, that is d by 2 dou square w by dou x square whole square plus dou square w by dou y square whole square plus 2 nu into dou square w by dou x square into dou square w by dou y square plus 2 into 1 minus nu into dou square w by dou x dou y whole square into delta x delta y. When you try to rearrange all these terms, you are going to get this equation, which is very, very important, and this equation is nothing but the final equation for the strain energy which is subjected to bending and twisting, and that equation is given by d by 2 into dou square w by dou x square plus dou square w by dou y square whole square minus 2 into 1 minus nu into dou square w by dou x square into dou square w by dou y square minus of dou square w by dou x dou y whole square into delta x delta y. So this is the strain energy equation which we have to remember for solving the problems. So, and for the total strain energy, so this is written for the element, and if you try to write for the element, complete element, that is A cross B, the total strain energy is written as U equals to d by 2, and then we take the double integration from 0 to A and from 0 to B, and we'll rewrite this equation. So this is the total strain energy of the thin plate which is subjected to bending and twisting. Okay, so this is the further modification. When you try to, if there is no shear load that is act, then you can substitute mxy is 0 and the form of the equation is reduces to this equation. And next we are going to see the potential energy of the transverse load. So potential energy of the transverse load you can see here. Similarly, we will consider the element delta x into delta y of a transverse load which supports a load of q into delta x into delta y. And if the displacement of the element is normal to the plate is w, and then the potential energy delta v of the element referred to the undeflected plate position can be written as what we have is delta V, that is you can written as load into deflection. Load into deflection. So, and again we'll consider that as negative potential energy, and therefore the total potential energy V of the total load on the plate is given in the similar manner. So, for the total potential energy, and the delta V becomes V, and then we are going to take the integration, that is minus of 0 to A, 0 to B, because it is the A cross B plate, and the load into deflection. So, load is again W, and the deflection is nothing but Q, because Q is the transverse load which acts per unit area. So, you have to take Q into delta X into delta Y. You have to multiply with the elemental area. So, therefore, the total potential energy V of the total load on the plate, that is given as W into Q into delta X into delta Y. So, this is the total potential energy of a transverse load what we have. Okay. So, in the previous one we have seen the strain energy which is subjected to bending and twisting, and here we have seen the potential energy of the transverse load.